Assalamualaikum warahmatullahi wabarakatuh and good evening. My name is Muhammad Fuad bin Omar. Now I would like to present about design of low-cost brushless DC motor using finite element method for automatic gate application. There are some common problems faced by users related to automatic gate. Damage to the motor caused due to water, pests, and other items. Cost. The choice of motor type is important because it will have a big impact on the maintenance price and energy consumption of the machine. The brushless motor are generally preferred in industry compared to induction motor. The brushless motor are divided into two types, that's namely permanent magnet synchronous motor (PMSM) and the permanent magnet brushless DC motor (PMBL-DC). PMBL-DC motor is attracting much interest due to its high efficiency, high power factor, high torque, simple control, and lower maintenance. PMBL-DC is preferred because it saves abundant energy. In this design, PMBL-DC motor is used for this barrier gate application because this motor type rapidly gaining popularity. The material used for the design of the motor will affect the price of the motor and hence the price of the barrier gate. Most motor designs use ferromagnetic material such as iron, nickel, and cobalt. If the use of this ferromagnetic material can be reduced, it can affect the price of the motor to become cheaper. The use of non-ferromagnetic materials such as 3D printing plastic certainly has advantage in terms of reducing the price of the motor. Next is the objective of this study. First, to design low-cost BLDC motor by reducing ferromagnetic material using ANSYS Maxwell for barrier gate application. Second, to simulate the electromagnetic performance such as magnetic flux density, flux linkage, back EMF, and torques of the designed BLDC motor. Third, to evaluate various models of the designed BLDC motor for final selection. Next is overall methodology. This is the flowchart for overall methodology to design the motor. Start with determination of motor parameter and ending with evaluate the best motor. For design the basic structure or geometry of this motor using the CAD modeling, while to operate the motor and analyze the motor with using FEM modeling. In this study, they have 6 design of motor according to the 3 sizes of permanent magnet, and each size have 2 type number of coil as shown in table 3.5. Next, determination of parameter. Figure 3.2 is the basic structure of the BLDC motor design in this research. Figure 3.2a shows the front and side view, while Figure 3.2b shows the structure of sizing. By reducing the ferromagnetic material, the rotor of the motor design uses the plastic material. Table 3.1 here shows the parameter motor structure. And Table 3.2 varied parameter for BLDC motor. The influence of flux linkage was noticed in this simulation for all models with a zero input current condition. Figure 4.1 depicts the motor flux linkage for a permanent magnet with a size of 12 × 2 mm. It shows a 3-phase sinusoidal waveform with a maximum flux linkage of 0.1274 Weber. From Figure 4.1, the value of maximum flux linkage is recorded and presented in Figure 4.2. From this result, it can be concluded that the size of the permanent magnet and the number of coils have an impact on the flux linkage value. In this analysis, the back EMF from all models has been observed with zero input current. Figure 4.3 shows the back EMF of the motor for permanent magnet size of 6 × 2 mm with 82 coil turns at 2000 RPM. It shows the maximum back EMF achieved at 256.09 volt in balanced 3-phase sinusoidal waveform. From Figure 4.3, the maximum value of back EMF Based on various size of permanent magnet, number of coil and speed of motor is recorded by figure 4.4. Figure 4.5 shows the result of magnetic flux density distribution in simulation for 12 × 2 mm size of permanent magnet, 82 turn coil, and 10 ampere of input current. The highest value of flux density point reached up to 1.906 Tesla. The highest value of magnetic flux density by the all model has been analyzed and recorded in figure 4.6. Each of the model has been analyzed with various input currents starting from 2 ampere to 10 ampere input current. The value of flux density has been compared with different size of permanent magnet 6 × 2 mm, 9 × 2 mm, and 12 × 2 mm, and number of coil n equal to 36 and n equal to 82. Next, dynamic torque. Dynamic torque is the actual process that needs to be incorporated into the resulting BLDC motor. Through the process, the torque value is measured to see the design capability of the motor. In this study, the motor torque average value was measured based on a speed of 2000 rpm. Figure 4.7 shows the torque value generated through the motor design simulation with size of permanent magnet 12 × 2 mm and 2 type number of coil n equal to 36 and n equal to 82 with the input current 2 ampere. Figure 4.8 shows the value of torque produced by 2 types of number of coil n equal to 36 and n equal to 82 with different size of permanent magnet 6 × 2 mm, 9 × 2 mm, and 12 × 2 mm, and the current value was adjusted from 0 ampere to 10 ampere. Result selection. Based on all of the previous performance analysis, these sections explain and conclude the best criteria for the final model, the performance characteristics that are being considered before the best model is selected are flux linkage, back EMF, magnetic flux density, and torque. They have 6 types of motor design models were produced and compared as shown in table 4.2. Based on the data obtained, all the motor design with the number of coil n equal to 82 have the better value flux linkage, back EMF, magnetic flux density, and torque value compared to the motor design with the number of coil n equal to 36. The value of magnetic flux density at current 2 ampere and speed 2000 rpm for all motor design with the number of coil n equal to 82 has produced value exceeding 0.9 Tesla. For the comparison of torque value produced by all BLDC motor designs, the reference value met is at the input current 2 ampere, but the target torque is 2.5 Nm. Based on the torque value obtained, all the BLDC motor design with the number of turn n equal to 82 have reached the desired torque target, while all the design with the number of turn n equal to 36 do not achieve the torque target. Therefore, based on the evaluation map, BLDC motor design with magnetic size 6 × 2 mm n equal to 82 is the best design because this design has fulfilled the torque target and also have good flux linkage, back EMF, and magnetic flux density. In addition, the size of the magnet for this design is smaller than the others, and it will give an advantage in terms of motor weight and cost. As a conclusion, first, the analysis of motor performance by using ANSYS Maxwell is based on magnetic flux density, flux linkage, back EMF, and torque. The size of the permanent magnet and the number of coil have an impact on the flux linkage, back EMF, torque, and magnetic flux density. The value of the back EMF changes in direct proportion to the speed of the motor. The torque and the magnetic flux density increase by increasing the value of the current. In terms of performance characteristic, the BLDC motor with a magnetic size of 6 × 2 mm and the number of coil of n equal to 82 is the best design and achieve the target.